Hello guys, welcome to DHP NIT Andhra Pradesh. My name is Arun Kumar and today we are going to discuss about wavelet analysis of images. The main topics which we are going to discuss today are two-dimensional discrete wavelet transform, multiscale analysis of images, fast two-dimensional wavelet transforms. Along with this, we are going to discuss about inverse wavelet discrete transforms, and at last we are going to discuss about denoising and compression of images using wavelet techniques. So to calculate two-dimensional discrete wavelet transform, we would be requiring a two-dimensional scalar function. This is required to know the trend of an image. Along with that, to know the details of an image, we would be requiring the image intensities along the vertical edges, the horizontal edges, and along the diagonals. We all know that any grayscale image can be represented as a matrix, and by modifying this matrix, we can modify the original grayscale image. But first, we can even generate complex images using a few lines of code in MATLAB. For example, these both images, the image on the left and the image on the right, were generated using few lines of MATLAB code. As mentioned before, we can generate 8 by 8 matrix and we can convert it into a grayscale image. So that is what we are going to do here. This function floor 256 into random of 8, 8 will generate random intensity values ranging from 0 to 255 in a 8 by 8 matrix. Then we are going to plot that. We can even modify it. So we are making all the elements of fourth row as 0 and all the entries of second column to maximum intensity values, except this, the 4, 2, which we are making it as 128. So by plotting, we will get these two images. The first one is the original image, which we got by using the function floor of 256 into random 8, 8. Here we got random intensity values ranging from 0 to 255. But by modifying it, we made all the row elements of 4 to low intensity values and all that of column 2 as high intensity values, except the 4, 2, which we have given the value of 128. Before going any further, I want to discuss briefly about CDF to come to wavelet transform. This is different from a regular Haar wavelet transform, and this is useful for us as we can generate an analysis matrix and synthesis matrix from it, which would be useful for us to calculate two-dimensional discrete wavelet transform and two-dimensional inverse discrete wavelet transform. For a regular Haar wavelet transform, this is the trend. But for CDF 2, 2, we are going to have weighted elements, and we are going to consider the elements which are far left and far right. Along with this, even the detail coefficients are different here. For a Haar wavelet, this is just the subtraction of the element before and after. But here, we are going to consider the element before that element and the next element also. We are going to have three main steps here. The first one is the prediction step, then we are going to have the update step, at last we are going to have the normalization step. In prediction step, to find P, we are going to apply linear transformation using the detail coefficient here. First, we are going to split the original signal into even terms and odd terms. Then, by using the detail coefficient from the CDF to come to transform, here we are having x even, and this element is x even shifted by 1 to the left. So by simply taking out x even as common, we are going to have x odd minus half into identity plus shift by 1 to the left into x even of k. Here we are going to represent p equal to minus 1 by 2 into identity matrix plus shift by 1 to the left. This is the prediction step. Next we are going to have the update step. In the update step, what we are going to do is we are going to build the trend using even parts in combination with some amount of detail. As you can see here, we are having the trend, but what we are going to do is we are going to represent it in terms of details, d of k and d of k minus 1. From this, as you can see here, this represents shift by 1 to the right. So by taking d common, we are going to get x even of k plus u into d. Here U represents the update step, which is given by 1 by 4 into identity matrix plus shift by 1 to the right. The last step is known as the normalization part. Here, in normalization step, we are going to normalize the trend by simply multiplying it with a diagonal matrix given D. And as mentioned before, we are going to have two matrices. The first one is the analysis matrix, and then we are going to have a synthesis matrix. In analysis matrix, W is given by D into U into P into split, and synthesis matrix is given by merge into P inverse into U inverse into D inverse. Simply, you can say synthesis is an inverse of analysis. Here, split is used to split up the given matrix into even and odd terms, and merge is simply the orthogonal inverse of matrix split. So one scale wavelet transform of image is nothing but a simple 2D discrete wavelet transform of an image. To do that, we are going to require an analysis matrix WA, which we can generate as we saw earlier, and along with that we are going to need a test image X, which can be generated using this function. So this is the original image, that is, this is the test image we are going to use. By performing one scale wavelet transform on the image, we are going to get Y. Y is given as analysis matrix into original image matrix into transpose of the analysis matrix. But here in Y we'll get four components. The first one is the trend, which is given as A into X into A bar, and vertical detail and horizontal detail along with the diagonal detail. Here A and B are matrices, which I'll show you in a moment. We can generate A and B matrices by simply splitting the analysis matrix WA. Here A and B are matrices of size n by 2 cross n. So by that we are going to get WSS, WST, WDS and WTD. As mentioned in the first slides, WSS is the trend component. Next we are going to get the image. So this is the output image Y we are going to get. This is YSS, this is YST, this is YDS and this is YDD. Next we are going to calculate the multiple resolution of an image. In multi-resolution of image, we are going to simply calculate the 2D inverse discrete transform. In 2D inverse discrete wavelet transform, we are going to use the synthesis matrix. By having the output Y, we are going to calculate the original image X. This is done by X equal to WS into YS transpose. Here similarly we are going to get four components of X: XSS, XSD, XDS, XDD, each representing trend, vertical detail, horizontal detail and diagonal detail respectively. To get the original image back, what we are going to do is we are going to sum up all these individual components. X equal to XSS plus XSD plus XDS plus XDD. This is the function which we are using to generate the original image back. But here, as you can see, we are having two matrices C and D. In analysis, we are having A and B of size n by 2 cross n. But here we are going to have CD matrices of size n cross n by 2. Here C and D are split vertically, there A and B are split horizontally. Next, we are going to see the original four components of the image. This trend and the before trend are slightly different, as that is the trend of the output image and this is the trend of the input image. By adding these four, we are going to get the original image back. So this is the original image. The next thing we are going to discuss is image compression and multiscale analysis. Before calculating image compression and multiscale analysis, what we are going to do is we are going to take an image. This image is known as Lena image. So here we are going to perform one scale CDF transform on linear image. Along with that, we are also going to find out the edges. So in this function, as we saw earlier, using analysis matrix, we are going to generate output image y, and we are going to adjust the brightness of an image to be visible for us. And here, next we are going to calculate the edges. To find out the edges, what we are going to do is YD, we are taking an matrix YD, which we are equating it to y, and now YD has all the elements of y. The first 1 to 128 and 1 to 128, which represents the topmost left corner images, the elements along this in this region, which represents the trend of an image. So what we are going to do is we are going to equate all those images, all those entries to 0. By doing this, what we are going to get is we will be having 3 detail coefficients in the matrix and no trend components. By having inverse discrete wavelet transform, we are going to get edges of Lena. As there is no trend, we are only going to get a summation of details, which is simply edge. If you observe carefully, you can find out this is the trend of an image. The component here, if you observe carefully, you can see the vertical edges. These are the horizontal edges, these are the vertical edges, and these are the diagonal edges. As mentioned before, by removing this trend and by adding these 3 details, we are going to get edges. As you observe carefully, you can find out all the edges in the image here. So now we are going to discuss about image compression. So image compression is one of the usage of wavelet transforms. During an image compression, we are going to fix a threshold value. Here we are going to fix a threshold value of 30, and what we are going to do is we will make all the entries which are less than 30 as 0. We will equate them to 0 in YD, where YD is the detail matrix, not the original matrix. Y is the original matrix which contains trend and details. YD is just the detail matrix. So in detail matrix, we are going to have a threshold value and we'll equate elements which are less than that threshold value to 0. By doing this, we'll be having less details in the image, and after that we are replacing the 128 into 128 upper left block, which is this block as we discussed it earlier. This block, the upper left block, which we have equated earlier to 0. What we are going to do is we are equate all the elements there to YSS. Here YSS is the trend block. By doing this, we are having all the entries of trend, but we are only having some detail components, as majority of the detail components are equated to 0. By calculating the inverse, we are going to get compressed image. So by using threshold function, we are making all the elements below 30 as 0. Intensity values below 30 as 0. After that, we are making the upper left block, which is 1 to 128 and 1 to 128 rows and columns to YSS, which is the trend block. By doing this, we will be having all the elements of trend, but only a few detail components. And by calculating the inverse discrete wavelet transform by using the synthesis matrix, WS represents the synthesis matrix. So by doing this, we'll get the original image back. We'll get the original compressed image back. And here, as you can see, we can even calculate the compression ratio. What we are doing is, first we are going to calculate the non-zero entries in Y, which is the original image. Then we are going to calculate non-zero entries in YC, which is compressed image. We are going to make them sum, that is we are going to find out the total non-zero components in Y and total non-zero components in YC. After that, we are calculating the ratio Y by YC. So this is the compressed image and this is the original image. As you can see, the compressed image is of a bit less resolution. If you observe carefully around the eyes, you can see it clearly. The next topic we are going to discuss is the errors. So as you can see here, we can calculate mean square error by using the formula norm of x1 minus x2 whole square by 2 power 16. Here x1 is the original image and x2 is the compressed image. By subtracting them and squaring all the entries and dividing it with 2 power 16, which is 256, that are the total number of entries, we can get the mean square error. And along with that, we are going to calculate PSNR. PSNR is the peak signal to noise ratio, which is the ratio of maximum power of an image to the power of corrupted noise. And we are going to calculate it in decibels. So now we are going to calculate the two scale analysis of an image. We have already calculated one scale of analysis of an image. There we got four components, YSS and three detailed components. So here what we are going to do is we are going to perform one scale analysis again, but only on the image, only on the trend of an image. Here YSS is the trend of an image. So we are going to perform one scale on one scale analysis on YSS. And we are going to plot it in the range of 1 to 128 and 1 to 128. So if I show you the image in the next slide, you will understand it clearly. So earlier we only had four components, one trend component, three detail components. You can even observe it here also. This is the vertical edge, horizontal edge, and diagonal edge, diagonal detail components. And here earlier we had the trend component, but here if you observe it, we have four components here. This is the trend component and this is the vertical edge of the trend, earlier trend component. So we have performed one scale analysis on the trend component. By doing this, we got two scale analysis. So we have already seen the two-dimensional wavelet transform and two-dimensional inverse wavelet transform, but using analysis matrix and synthesis matrix. But these two methods are impractical because to find out the output y, every time we have to multiply it with w into x into w transpose, and each one of these matrices is of the size n into n by n matrices. So we are going to have an order of arithmetic operations n cube, which is not desirable. So what we are going to do, so similar to a one-dimensional wavelet transform where we have two channel filter bank method, we are using the same method here using simulets. Simulets are nothing but symmetrical wavelet. So in filter bank methods, we are going to have four components. The first one is H. H gives the non-zero coefficients of low pass filter along the analysis transform, and G gives non-zero coefficients of high pass filter for analysis transform. So this is G and this is H. Similarly, we are going to have RH here, which gives non-zero coefficients of low pass filter for synthesis transform, and RG gives the non-zero coefficients of high pass filter for synthesis transform. This gives us RG. In the next slide, we are going to discuss a detail. So we are going to have a function called simulets. Simulets of 24 indicates we are going to have 24 non-zero coefficients in H, which is low pass filter, G high pass, low pass, and high pass. So what is the difference between H and RH? What is the difference between the low pass filter of analysis transform and low pass filter for synthesis transform? Similarly, what is the difference between high pass filter for analysis transform and high pass filter for synthesis transform? So I am going to plot these four graphs. After observing it, we'll get a clear idea. So first what we are going to do is we are going to plot all these four functions. Later we are going to load our image, Lena image, after which we are going to calculate 2D discrete wavelet transform using this function. So here we have the four components here. As you can see, the low pass analysis filter and low pass synthesis filter are just but the mirrored signals of each other. Similarly, a high pass analysis filter and high pass synthesis filters are mirrored signals of each other. This is H, this is RH. Similarly, this is G and this is RG. So by using filter bank method and 4 components, the R, G, RH and RG, we have calculated a function which will generate one scale similar transform of an image. As you can see here, this image is same as that we have calculated using y equal to wx w transpose. There the order was n cube, but here we have calculated it in a much faster rate, and we have got the same image. We have the trend here at the upper left corner, then we have the 3 detail coefficients, the vertical, the horizontal and the diagonal coefficients. So to find the multi-scale analysis of an image, what we are going to do is we are going to find out the trend, then we are going to find out the details, and by using the trends and details we are going to get back our original image, except here we are doing it for 2 scale multi-resolution representation, which implies for a by having a 2 scale trend and 2 scale detail, what we are going to get this image is nothing but trend of 1 scale. I'm going to show it with diagrams. So as you can see here, this is the trend of 2 scale multi-resolution representation, and this is the sum of details. So what we got here, as mentioned above, if we sum all the detail matrices, we are going to get edges. As you can see here, we got the edges. So by adding both the trend and details, we got the trend of 1 scale. This is not the original image. This is the original image. This is the 1 scale representation of the original image. So by taking this image and by doing 1 scale, we are going to get 4 functions: the trend, and these 3 are details: vertical, horizontal and diagonal. So this is the trend we got by applying 1 scale representation, and the before both trend and details are trends and details of this image. So by applying 1 scale on again on the trend here, we are going to get a new trend and new detail coefficients. So how many times we have did it? We have applied 1 scale image on the original image, then we got the trend, then we have applied 1 scale image on 1 scale wavelet transform on the trend, then we got 2 scale multi-resolution representation. Denoising and compressing of images using wavelet techniques. So this is the last topic of the video. As you can see here, we can generate a noise similar to how we have generated an image using this function, and then what we are going to do is we'll add the noise to our image, then we'll plot it. Then we'll remove the noise by using wavelet techniques. To do that, first we need to find out the wavelet transform of an image, then we'll to get the trend and detail matrices, after which we are going to calculate the ratio of maximum element in trend by maximum element of detail blocks, combined detail blocks. Detail blocks has 3 matrices: the vertical, the horizontal and diagonal. So maximum of these 3 and the maximum of trend. By calculating the ratio, if the ratio is high, this implies we can equate most of the elements of the image to 0. By doing this, we'll compress the image. Earlier we have seen it. By having a threshold value and making all the elements, and by equating all the elements to 0, we have compressed the image earlier. So similarly, we are going to make if the ratio is large, then we are going to set a large portion of the entries to 0. By doing this, we are going to have a compressed image with some less noise. So these are the functions. This is the fast discrete wavelet transform. By doing this, we got YSS, and then we got YDD. YDD is the detail block, YSS is the trend block. Then we are going to have the maximum of this trend block, maximum of the detail block. We are going to find the ratio. If the ratio is high, we are going to, according to these calculations, what we got is about 95% of the entries we can make it as 0. So that's what we are going to do. By eliminating 95% of the pixels, that is 95% of the entries. So 95% of the entries of the image yn, we are making them as zeros. After that, we are going to apply inverse discrete wavelet transform. Then we'll get a denoised image. I'll show you both the images in a moment. So as you can see here, if you pause and observe both these images, this image has a lot of noise, but here, by setting large portion of the entries to 0, we have decreased the noise in the image, and we have even compressed the image. So in today's video, we have discussed about two-dimensional discrete wavelet transforms. First, we saw about how to convert matrices to images and images to matrices. Then we have discussed about CDF 2,2 wavelet transform. After that, we have performed one scale wavelet transform of the images by finding analysis and synthesis matrices. After performing those two, we have used the Lena image to calculate one scale analysis. Then we have performed image compression. Then we found out the mean square error, peak signal to noise ratio. After that, we have performed two scale analysis, not one scale. We have performed two scale analysis. Later, we have calculated the fast 2D wavelet transform. After that, fast 2D inverse wavelet transforms. We have seen four simulets: H, G, RH, and RG, which are components of analysis transform and synthesis transforms. Low pass filter, high pass filter, low pass filter, high pass filter for analysis and synthesis transforms. Then we have calculated the multi-resolution representation, where we have found that by using the trend and details of two scale images, we have found the trend of one scale image. If we have the details of one scale image, then we can even find the original image back. Then we have discussed about adding noise to an image. Then we saw how to remove the noise of a image by using wavelet techniques and compressing the image. So these are the topics which I have discussed today. Thank you guys. That's it for today. Thank you so much guys. I'll provide timestamps for this video.